No one has joined the meeting. I'll wait for 5 minutes. Then I'll start. Yeah, we'll wait for 5 more minutes for other people to join the class. Then we'll start today's class. Okay. Hello everyone. It's already 6:05. We'll start today's class. I'll share my screen. Are you able to see the screen and listen to me carefully, clearly? Okay, thank you. Mm. So we'll start this lecture number 10 of this material characterization course given by Professor S. Sankaran from IIT Madras. And this is me, Dorothy Sachdeva. I am doing my PhD from Material Research Center at Indian Institute of Science. So till now we have learnt a lot of things about the microscopy. And in last 2 or 3 weeks, we have been studying about the diffraction and the reflections which are allowed and which are not allowed, and so on. And in this today's lecture, we'll mostly study about the TEM and different techniques, different imaging which we can do in the TEM itself, the diffraction or in the TEM mode, and also we'll study some of the basics about the STEM part as well. And then we'll do the quiz and practice assignment of this week. So let's begin. So basically, TM is a great instrument which is capable of doing imaging, diffraction, chemical analysis, and spectroscopy. Imaging is just basically used for the direct analysis of the sample. You can predict certain things using this imaging technique. Using this diffraction, we have seen in the previous classes as well, you can study about the nature of your sample, if it is crystalline, polycrystalline, single crystalline, amorphous, and so on. And this chemical analysis will tell you about the sample, which atoms are present, in which state they are, and so on. And this spectroscopy will also tell you about the types of atoms which are present in your sample. So TEM itself can do different techniques, including all these, which can be used for the analysis of your sample. So from the same area of your specimen, you can have these different techniques which can tell you about your specimen. However, be aware of artifacts due to projection. Like in SCM, we used to get topography information. Like in EBSD, we used to get different orientation of the specimen, of the sample, how they are oriented, and so on. But this TEM, this gives only 2D projection of the sample. So, like this image shows that it seems like it is a two-face rhinoceros. Like one face is this and one face is this, and this is a single rhinoceros. So this TEM will just give you a 2D projection of this. But in actual, these are different rhinoceros. Like one is this one and the other is this one. So you can't predict using the TEM images, but by seeing this image, you can't predict if it is a double-faced rhinoceros or these are two different rhinoceros. So this is the just a disadvantage of your TEM, that you can't predict. these things. So interpretation of TEM is not a straightforward technique like in SEM, because in SEM, if we are having some flower kind of things, then you will see that the flowers are easily visible in your SEM image. But in TM, it will be just a black box. So you need to analyze. So the analysis of these TEM images are not straightforward. And also, if you have done the poor sampling, like this TEM, the electron undergo transmission. So for transmission, your sample should be, just a second. Yeah. Yeah. For the transmission, your sample should be thin enough to pass the electron beam through the sample, through it. Let me admit. So if you have prepared your sample which is very thick and which can't allow the electron to be transmitted from the specimen, if it is thin then it will be transmitted, but if it is thick like this then it won't be transmitted, so you won't get good TM data. So your sample should be thin in the range of, if you do fibbing and all is used for thinning of your specimen, to thin the specimen. So in that case, we keep the sample thickness around 50 to 70 nanometer. This is just an average, or just a rough estimate. Also, as the SCM, this was one part, and the next part is in SCM, basically we do imaging in lower kV. That means lower energy of electron is being used. But in TM, higher kV is used. So it means high energy of electrons might damage your specimen. Just a second, let me admit some students. Yeah. So high energy of electrons might damage your sample. So these are just basic things maybe you need to remember for your TEM. Like the interpretation is not straightforward like SEM. If you have poor sampling, then also you won't get good data. Also, there is a possibility of radiation induced damage. Because of the higher kV, the high energy of electrons can damage your sample, and you can have features which correspond to the damaged part and not to the actual features which you were looking for in the sample. So you need to keep in mind, if your sample is being damaged, you need to acquire your TM at a lower kV. So depending upon your sensitivity of your sample, but generally the kV of the TEM is fixed. They change because if you need to change the kV, then you need to change all the alignments, starting from the condenser lens to objective lens, and all the alignments of the TM need to be changed. So generally TM is operated at a constant kV. But if you need to have lower kV, then all the alignments need to be changed. Let me clear this page. If you have any doubt, please let me know. So the capabilities of the modern TEM. Firstly is the imaging. This firstly we'll discuss about the technique of each technique and then the information which is provided by the technique. So firstly the imaging. So imaging is basically conventional diffraction or absorption high resolution phase contrast imaging. High resolution imaging can also be done and phase contrast imaging can also be done. And that will tell you about the atomic structure of a perfect and defected crystals. So if your crystal is defective, you can tell about the crystal through your high resolution imaging and so on. And the diffraction can be taken from basically we use this selected area diffraction, which we generally call as SAED, selected area electron diffraction, selected area electron diffraction. This we'll discuss in today's class in great detail. So this SAED pattern will tell you about the phase identification, the relative orientation of grains, the phase defect characterization. All these things can be examined or can be analyzed through this selected area electron SAED patterns. Also, we can have this micro diffractions. Micro diffraction will be taken higher from a different region of the sample. So this will tell you about the orientation and phase identification. Also, we discussed in the first lecture of your TM that we can also have this convergent beam diffraction, where the like in the SAED, you will have some spots feature. Like if this is your central spot, then you will have your diffracted spots like this, and the second one is your conventional beam electron diffraction, which is known as CBED. So in that case, the single spot will also have the Kikuchi lines within themselves. So that is known as your CBD. We'll discuss about this in some detail in the coming slides. So in CBED, the diffracted this pattern will not have some specific spots like in the CBD. Each spot will also tell you a lot of information about your specimen. So it will tell you about the CBED will tell you about the point group and the space group, the strains, the interatomic potentials, and so on. Next, we have the spectroscopy. Spectroscopy, you can have EDS, which is known as energy dispersive X-ray spectroscopy, or we generally write is at EDS, energy dispersive X-ray spectroscopy. It tells you about the composition, sometimes the location of atom in the unit cell. So basically, EDS will tell you which atom is present at that location. Also, nowadays the technique have improved so much that you can have atomic resolution EDS, atomic resolution EDS mapping, where if you have a spherical thing, your sample, and you have a shell over it, of different atom. Suppose the inner one is Z1 and the outer one is Z2. Then you can do the EDS mapping at this intersection. There you will be able to clearly see that this one will show your Z1 and this one will show your Z2. So you can easily differentiate between the atoms positions also. And the next one is the EELS, which is the electron energy loss spectroscopy. So EELS tells you about the composition, bonding and coordination. And next one is the next technique is the in situ microscopy. So in situ microscopy, we can do heating and cooling just by having your heating and cooling. Suppose if your specimen, you need to study how the phase or how the composition or anything changes upon heating or cooling the sample. So you need to have a specific holder for that case, where your holder itself will start heating and cooling, and and then you can do imaging in between the. I have a question in the chat box. AFM and SCM TM technique, which is the high resolution? These are all different techniques. If you are talking about the resolution only, then TM will give you the highest resolution. SCM is basically used for the morphological kind of things, for the topological information, not for the high resolution thing. For the atomic resolution, this SCM and this TM is used. And even after TM, we have one another technique known as STEM. This we'll discuss in later class, which is scanning transmission electron microscopy. So this STEM gives you the atomic resolution. Like it can directly, I'm writing it on the left side of the screen. Like if you have the STEM data, it can directly tell which atom is present. Suppose this is the vacancy over here, so it will directly tell you. So this STEM shows the atomic resolution, and among these your AFM is used for the AFM technique which you are talking about is used for the height and other measurements of the sample. So it's just the probe which is moving from the one region of the sample to another to tell you about the height and other things like the topographical things. But if you're talking about the resolution, then TM will give you the highest resolution among all. Fine. Any other doubt? Okay. Then yeah. So for in situ, you can also study your deformation, which will tell you about the mechanisms of your slip and fracture in your sample. Like metallurgical people will use these things. Also, you can have some controlled environment, like you can pass some gas. Nowadays, there are different EM holders for the in situ techniques, which can directly pass a specific gas which will react with your specimen, and then you can see what changes are occurring in your specimen, and then you can image that during the conversation process itself. So this controlled environment can be used for the oxidation and catalytic reactions on its own. So these are all the techniques, basically the imaging, diffraction, spectroscopy and in situ microscopy, which can be used to get a lot of information about your sample. If there is any doubt, please let me know. Otherwise, we'll move forward. Okay, I don't see any raised hands or any comments, so I'll move forward. So there are different types of diffraction pattern. Like in your XRD, we studied that there are different kind of X-ray diffraction, which were like this for the gaseous phase, this for the liquid and amorphous phase, and for the crystalline, we were getting these sharp peaks. Remember? So similarly, this diffraction pattern in TM will also, sorry. So similarly, the diffraction pattern in TM will also tell you about the nature of your sample. So if your sample is amorphous and is not having the long range order and all, if it is amorphous, then you will have the diffraction pattern similar to this one, where you will have the some blurry kind of thing with this one as your, this is your direct beam, and the rest one is completely diffused one. So you can't predict much information about this. And next one, you have this crystalline sample. This one, the second one, where you will have your single spots, single crystalline. So it will tell you about your specimen that it is single crystalline. These single spots in your diffraction pattern will tell you how your specimen is oriented, and it will also tell you that your specimen is crystalline. So these different spots will tell you about your different family of planes. This we'll discuss later on. This is your direct beam. This whole one is your direct beam. Sorry. And all these are your diffracted beams. We'll use this for further imaging. So please remember this crystalline diffraction pattern, where your central one, the bigger one, is your direct beam, and the rest all are your diffracted spots. Also, you can have the fine grains, where you will have a direct beam, which is this one, and then you will not have these uh, different spots as in the crystalline sample, but you will have these rings kind of things. So this will tell you about that your sample is not having the single crystalline nature, rather it is fine grained sample. So these rings will tell you that your sample is fine grained. Also, after this single crystalline, you can also have this CBED, where each spot is not only a spot, rather it tells a lot of other information about your specimen, and you can see that each beam, direct beam is also having the Kikuchi lines. If I'll zoom it, I guess you can see it much more clearly, that you can see these diffracted lines, these Kikuchi lines within the sample, right? And also in the diffracted spots also, you can see the similar kind of Kikuchi lines like this. So this is your CBD, convergent beam electron diffraction. So this is basically the ray diagram for imaging and diffraction. The first two things which we discussed in this technique, the imaging and the diffraction. So basically, firstly, you have the electron source at top of the your TEM, and then the electron beam get converges through this condenser lenses, and then you have the object or specimen which is placed over here, and then the beam passes from object to the objective lens, follow, and then the beam get firstly converged at this location, and this location is known as your back focal plane. Please remember this. This is very important. Just pay a little attention. Let me zoom in and show you clearly. So basically, after your objective lens, your images get diffracted. So this diffracted at this back focal plane. Then you will have your first virtual image is formed over here, and this is known as the first intermediate image. And then after this, the rays will pass through the intermediate lenses between the objective lens and your projector lens. You can have multiple intermediate lenses. You can have multiple intermediate lenses in between your objective lens and your projector lens. And after that, your secondary intermediate image is formed over here, and you are just now expanding, or you can say just magnifying this image using this projector lens. And then you use this projector lens to magnify this image. So this is your final image, which is, so this final image is just formed firstly on your fluorescent screen. Then if you lift this fluorescent screen, then you can capture it using your camera. You can have different types of camera. Generally CCD camera is used, but there are multiple cameras. And in case of the diffraction, similar to the imaging, you will have your electron source as top, and then the electron beam will pass through the condenser lenses, followed by the rays will fall on the object, and then you will have this objective lens. And then after that, your all these things are similar only, but here your diffraction pattern will form. So we will see in the later slides that in what case we will get this image and in what case we will get this diffraction pattern. So what thing will be different in the path of your electron beam, that you are getting the image in one case and you are getting the diffraction pattern in the other case. So basically, just please remember this, that the this is the back focal plane, one thing, and the first intermediate image as the other important things from this slide. There are different operations in the TEM. Like in SEM, we used to do scanning where we used to have the fine probe, and this fine probe will move to your from one position of your sample to another, and then you will have the image which will do raster scan, and then one scan will be over, then you can see the complete image. But in TEM, there is no scanning. You will directly see in one single shot, you will see the complete image of your sample. So in this case, you does not have a fine probe, rather you have a parallel beam of electrons which are falling on your specimen. So for parallel beam operation, if this is your central axis, is your optic axis, this one, then after this electron beams are passing through, firstly passes through the C1 lenses, then the C2 lens, if the C2 lens is under focused, then your electron beams will have will be will give you under focused beam. But if your C2 lens is focused, then it will focus your electron beam at this point, and then after that you can have the upper objective lens. Like your objective lens can have upper objective lens plus lower objective lens. So one upper objective lens will be located, if this is your specimen S1, then this will be your upper objective lens, and this will be your lower objective lens. So you can have your upper objective lens after the C2 lens. So the rays will be parallel after they are emerging from this upper objective lens, so that in the specimen you are observing this parallel beam. So for the TEM, the more the parallel beam, the better is the imaging. So depending upon which technique you are using, like we discussed, there are different techniques. So depending upon the technique which you require, you can have different modes. So you just need to change the strength of your lenses. So if you change the strength of your lenses, then you can have different path, or you can say different ways on which the electron beam is falling on your specimen. Fine. So this is basically says that C1 forms a demagnified image of the gun crossover. So C2 needs to form an under focus image of the C1 crossover for parallel illumination. Alternatively, C2 is focused. So to produce an image at the front focal plane, the upper objective lens is required. So if upper objective lens is not there, then your C1 should be under focused. But if your C2 should be under focused after the C1 crossover. But if your C2 is focused, then to produce an image at the front focal plane, then the upper objective lens is required. So for the parallel beam mode, C1 is kept constant setting, only C2 needs to be manipulated. This we have clearly seen from these two ray diagrams. We have just changed the strength of the C2 lenses, and we have seen that if the C2 lens is under focus, then you are having this parallel beam. These are also almost parallel only, but if your C2 lens is focused, then you need to have this upper objective lens to get the parallel beams of your X-ray which will fall on your specimen. So basically, the use of C2 aperture reduces the beam current. So you can also have your aperture at your C2 lens like this shown by this black one, these two. So these are just the C2 aperture which are used to reduce the beam current but increases the coherence of the beam. So the convergence angle will reduce. So as a result, your coherence will increase, but the beam current will reduce. So you will have to compromise among different things in your TEM. If one thing is getting increased, then other or some other thing will reduce. So in the end, you need to make a call, or you need to set the parameters such that you can get your optimum data. So this convergent beam mode works as such. So this convergent beam can be used as a probe. So basically, you have your C1 lens similar to the previous one, then you have the C1 crossover, then you have the C2 lens. So this C2 lens is focused, then you can get the focused beam, just a focused beam at your specimen. In the previous case, we used one other objective lens to make your beam parallel, but in this case, you need to have your focused beam. So this focused beam is used for this convergent beam mode. Basically, you can remember it as CBED, convergent beam electron diffraction. So this convergent beam can be used as a probe. This beam, converged beam itself, can be used as a probe like in SEM. So use a combination of lens settings and apertures to get this. With FIG is just the source of the electron. You can have different sources like we discussed in the initial classes of your SEM itself. Like you can have thermionic emission, remember? Thermionic emission, field emission. So this is basically your field Schottky emission. So this is basically your FIG. field emission gun. So with FEG, a fine probe can be obtained with C1 and C2. Otherwise, we require a C3 condenser objective lens. So you have different strength of lenses you can have, and depending upon the strength, you can use multiple lenses also. So this is you can also have your C3 lens also to get the fine probe. So if you switch off your C2 lens and use C3, so it will give a finer probe as compared to the rays where method where you use C2 to have your fine probe. So this diagram is similar to the previous one only, where your C2 lens is off, so all the rays which are going are not diffracted, they are just transmitting as such because this C2 lens is off in this case. So after that the electron beam are passed through C3 lens. So then the C3 lens will have a much more focused, a much more convergent beam as compared to the previous case where C2 was used for the convergence of the beam. This we use in further cases like STEM and all. Next, we will study about the effect of C1 lens strength on probe size. Till now, we have kept the strength of C1 lens as a constant value. Now we'll study how that the strength of C1 lenses will affect the probe size. So in this case, you will suppose this is your C1 lens, and if you have a stronger C1 lens, then the rays will be focused much closer to the lens, and then after the C2 you will have this small probe. But if you have the lower strength of your C1 lens, so it will get focused at a longer distance from the. Is there any doubt? I heard some noise. Is there any doubt? If not, then we'll move further. So if you have a very less strength of your condenser C1 lens, then you will have the focused beam which will be much further from your C1 lens. Then after passing the rays from C2 lens, you will have a larger probe in this case. So depending upon the strength of C1, so each and every factor will give its own contribution to the probe size, rather they are parallel or you are using the convergent beam. So every factor will have its own impact on the probe. It's not getting back. Next, I have discussed this condenser objective lens systems where you can have, suppose in this we will discuss about the strength of your C2 lens. In the previous one we discussed about the strength of C1 lens. In this case, we will discuss about the strength of C2 lens. So as the strength of the C2 lens, this is your C2 lens. The upper part we have not shown in this figure. Suppose as the strength of C2 lens will increase, the beam will go from, suppose if the strength of C2 lens is low, then you will have this parallel beam after passing through the C2 lens. Then you will have these twin lenses, intermediate lenses and all. And after that on your specimen, you will have the almost parallel beams like this case. But if your strength of C2 lens is increasing, then you will have the converge beam will be converged, then you will have a fine probe in this case. And if your strength is increased further, then your electron beam are converging at a much closer to C2 lens, then in this case you will have this divergent beam. This is the divergent beam. Then if you increase the strength of C2 further, this is the high C2 strength. This will be increased by increasing the current, because these are all the copper coils are there around the lens. So just by increasing the current, you can have the high strength of C2 lens. So after this high strength of C2 lens, and after these all the twin lenses and mini lenses, you will have again have this parallel beam. So depending upon the strength of your C2 lens also, you can have different either parallel or probe or divergent or parallel beam. So you are seeing different effects, effect of C2 strength, effect of C3, C1 and C2 and all. So next one is this shifting and tilting of the beam. Suppose this is your real source. Firstly, we'll discuss about the shifting and then we'll discuss about the tilting. Suppose this is your real source, and if your beam is getting diverged like this, and if you are shifting the beam, so you will just do the shifting from here to here of the gun. Then you can have just the shifted beam and all the things will remain same, like all the width and everything will remain the similar like the previous one. And if you are doing the tilting of the beam, suppose your real source was there and you are not shifting. Shifting means just the shifting. Tilting means you are tilting the beam. These two are different things. Just keep this in mind. And if you are tilting the beam, then you will have your uh, this was the previous, the real one, where the beam is spread at this location of your specimen. And if you are doing the tilting, then you are having the electron beam at the similar location, but your source is tilted. So it will have different effects on your imaging and all. Shifting will just shift your electron beam, and tilting will tilt the source of the electron, and you will have the electron beam on the specimen at the similar location only. So this shifting to a certain position on the specimen, if you are having, suppose your central beam is this and your region of interest of your specimen is somewhere here, then you will just shift your beam to have the data. Or you can have shifting of your specimen. You can move your specimen over here so that the region comes here, and then you can have your data. And in your tilting is basically used for the center dark field imaging. So basically in tilting, your source itself will tilt in such a way that you can have your, this will discuss in the center dark field imaging further. Also, then you have this C2 aperture alignment, where this, suppose this yellow one is your fluorescent screen. By seeing on the fluorescent screen itself, you can do alignment of your electron beam. Suppose if your beam is coming like this, then it is the distorted beam. It is off axis. Then you will change using the wobbling and other techniques in such a way that you will get this perfect circle at the center of the screen. So this will tell you that your be you will have your, you have your focused beam. So this is your distorted beam and this is your focused beam. So you can change the alignment of your aperture in such a way that when you do wobbling, your your centered beam will just go from here to here equally in all directions. So when you do wobbling, it should not go from here to here. It should go from central spot to it should expand in all directions equally when you do this wobbling. So usually there's a control that will introduce an AC current into the lens coils, in effect wobbling the lens setting either side of focus. This wobbler saves you from manually under-focusing and over-focusing the lens. But think what you are doing. So this wobbling will save your time. So you just need to converge and diverge your beam and see if you are getting the central spot is diverging equally in all direction, like in this case of it, or it is diverging like this. So if it is diverging like this, then you can use this wobbling thing, where it will automatically do under focusing and over focusing of the lens, so that it will continuously do this, and then you can use your hands to do correct the alignment of your C2 aperture. The next one is the effect of astigmatism. Suppose this is your optic axis, the center of your fluorescent screen. Your beam should be ideally should be circular and should be at the center. And if you converge and diverge it, you will get the convergent divergent beam, which should be equally spread in all direction. And if you are having this astigmatism in your beam, then you will have, if you converge diverge, you will have this distorted under focused like this one, or distorted over focused beam like this one. Ideally, which we what we saw in the previous slide, that it should, sorry, it should expand equally in all direction. But if it is having this elongated things, then there is a problem of astigmatism. Then you need to correct the astigmatism to get your circular beam, which should be circular and expand equally in all directions upon expanding, converging and diverging. So this is just a small description. Like if your C1 lens setting is smaller, then you will have a higher FWHM of your probe. That means your these are just the settings of the TM, where the C1 is number 1, that means your probe is thicker. And if you are having number 5, that means probe is thinner. And the convergence angle goes like this. Like if you are having a smaller aperture, and in one case you are having a bigger aperture. So if you are having a smaller aperture, then your convergence angle will also be small. Convergence angle is what? Basically the angle of the optic axis and this one. And if you are having a higher aperture size, then your convergence angle will also be higher. This is the alpha. Remember, no? This we have discussed in previous classes. So basically, focusing and height. This is something important. We cannot emphasize too strongly that we need to fix the height of our specimen on the optic axis. So we can always work at the same objective lens current and thus at a fixed objective lens magnification. This is really important and this fact is usually ignored. We cannot fix the height of our specimen on the optic axis. We always need to work on the same objective lens. We just need to change the strengths of your lenses itself. Okay, so these are just the elaborative things which we discussed in the previous slide. So basically this is your specimen. So this we have shown only after the specimen only. So this was your, remember I told you to keep that thing in mind, like this is your back focal plane, BFP. So at your back focal plane, you have this diffracted spots kind of thing. And this, if you are uh, having a aperture and sorry, and if these beams are passing on, and then you have this intermediate image, first image, remember this one, and if you keep the aperture at this intermediate image 1, then you will get the diffraction pattern. And if you keep the aperture at this back focal plane and remove the aperture from the intermediate image, then you will have the image. So remember this agenda, that if you want to get image, if you want to get image, then aperture should be at back focal plane. These are two opposite things. And if you want to get diffraction pattern on your screen, then you need to keep the aperture at the image plane. These two are different things. Just remember these things. So if you want to get an image, like in the second case, you need to get the image, then you need to keep your aperture in the back focal plane and you need to remove your aperture from the image plane. And if you want to get your diffraction pattern on your screen, then you need to put the aperture in the image plane and remove the aperture from your back focal plane. So these are two opposite things, and to get these two different diffraction pattern and imaging, you can have these different apertures at different locations. So just remember these things. This is a very important thing. Okay. So for imaging, your beam should be parallel and you will have the spatial intensity variation. So depending upon the interaction of your beams with the specimen, you will have different intensity and then you can have the image. And in your diffraction pattern, your direct beam will be like this, and then you will have the diffracted beam in all directions. So this will have your angular intensity variation and your image will show you the spatial intensity variation. So these are the for imaging, and this is for diffraction pattern, DP. So in DP, diffraction pattern, you will get the angular intensity variation, and in the imaging, you will get the spatial intensity variation. It is not getting. Next, you have the selected area diffraction in DM. So in this case, you for the selected area diffraction, you will not be having the aperture in the back focal plane. Rather, you will be having your aperture. This black one is always the aperture, which will block the outer beams and will allow only the inner beam, which are closer to the optic axis, to pass through them. So, to get the diffraction, you will get you need to have your aperture in the image plane. So this aperture is known as SCED aperture, because in the end you are getting the SCED pattern only, no? So this will be SCED aperture, which you will put in the image plane. So this selected area diffraction in TM. So we cannot insert, basically selected area diffraction. What does it mean? So that it means if your specimen is like this, suppose, and you want to get your diffraction just from a specific area of your specimen, then you cannot have the aperture on your specimen itself, because your specimen are very small in range, like those are in nanometer range, and you cannot have the aperture in nanometer regime and to align and all that, it is not possible. So you have this virtual aperture, which is kept just above the specimen. So this is your specimen. So to select a specific area from your specimen, ideally you should have the aperture on your specimen itself, but that is not possible at all. So in this case, you have a virtual aperture which is present just above the specimen in this case, and you have this SED aperture in your image to get the diffraction pattern. So we cannot insert the aperture in the specimen planes because the specimen is already there. So we can't put a aperture over there. And inserting an aperture in the image plane is like inserting a virtual aperture in the specimen plane, which restricts the area from which we get the diffraction pattern, because we are specifically selecting a specific area from your sample from which you want to get your diffraction pattern. So the smallest aperture is 10 micrometer. Demagnification is around 25. So selected area will be this one only. Okay. Then for the imaging, so this was about the diffraction, and for the imaging, you have certain bright field and dark field imaging, and you can have different type of dark field. So firstly, I will discuss about the bright field imaging. So in bright field imaging, simply remember your diffraction pattern. So consider this is as your diffraction pattern. So you will select only, so this one is your direct beam and rest all are your diffracted beam. So you will select only your direct beam to pass through, and then you will get the image which will be your pure bright field image, because bright field image tells you about the specimen and it will be just from the direct beam without any indirect beams. So you will put an aperture. So when while seeing this diffraction pattern itself, you will put an aperture in the direct beam, and so only the direct beam will pass like this, and all other beams, like all the diffracted beams, are blocked in this case, and only the direct beams are allowed to pass through this objective aperture, and then you will the imaging you obtained in this case will be known as the complete bright field image. And in the second case, suppose you select one of the diffracted spot and you put an objective aperture around it, so that only the diffracted beam is passing and all the direct beams are blocked by this objective aperture. So now the image which will be obtained in this case, it will be a dark field image, and you can have one more centered dark field image, because in this case, if this is your optic axis, this one, if this is your optic axis, then your diffracted beam is further from your optic axis, then you won't get that good quality of your image, because your diffracted beam which you are passing from the objective aperture is quite far from your optic axis. Then you can have this centered dark field. Centered dark field. In this case, you will tilt the incident beam itself. Like we discussed about the shifting and tilting, I told you that tilting will be used in the centered dark field. So in this case, you will tilt the incident beam. So earlier incident beam were coming like this. In this case, incident, just see very closely, incident beam is coming like this at a certain angle from the optic axis. So these tilted beams are getting converged and diverged over here from this objective lens. You will have your direct beam over here and your diffracted beam will be along the optic axis, because your incident beam itself is tilted. So as a result, if this is your optic axis, then the central spot here will be your diffracted beam, this one. Then you will put an aperture in your objective lens and you have selected the diffracted beam, so you will get your dark field imaging. So in dark field imaging, you can have the simple dark field and the centered dark field imaging. Both the things are there. So this is the basically the bright field image of your specimen, and this is the dark field. How can you say that this is a dark field and this is the bright field? Because in bright field, you are passing the direct beam. So your background will be white in this case of lower contrast, and your specimen which are blocking the direct beam will be appear dark. because no intensity is coming from your specimen basically in the direct beam because the specimen is blocking. So in that case, your specimen will be dark and your background will be white. So this will be a bright field imaging which is taken from the direct beam. Sorry, direct beam. And if your imaging is done from the diffracted beam, then you are taking the diffracted spots. The spots are being diffracted from your specimen. So if the specimen diffracted spot are taken, then thus diffracted spots are from the specimen, then your specimen will appear bright and your background will appear dark because background contributes only from the direct beam. So if you are not allowing the direct beam to pass through your objective lens, then you will get your background as dark and you will get your specimen as bright. And you can select different diffraction patterns are there. Suppose this is your central spot and you have different diffraction patterns. Suppose if you have selected once this one, then this region of your specimen, this one is appearing dark. Suppose if you select another diffracted spot like spot number 2 instead of spot number 1, then you might have the possibility that your this region of your specimen which were earlier dark appears bright in this case. So the diffracted beam which is, so this says this dark field image tells you, suppose if dark field image is taken from spot 1, this will tell you that the diffracted spot 1 have the contribution from only those regions which are appearing light or bright in this case. And if you are taking the dark field image from spot 2, and in that case this region becomes dark, this region becomes dark, and only this region becomes bright in case 2, then you can say that this diffracted spot number 2 is corresponding to this region. So you can have different information from different spots of the diffracted beam. Is there any doubt? Any comments? What is the order of resolution of SCM, AFM, TEM, and HRTM? TM and HRTM are, HRTM is basically the part of TM only. AFM, why are you getting confused between this? The same person is asking the order of resolution and or. AFM will tell you about the topographical information. So basically your resolution will go as such, and HRTM is basically the part of your TM only. HRTM, what does HRTM mean? HRTM is basically the high resolution TEM image where you will get the fringes. Sorry, let me make it much more clearer. In HRTM, you just get the interference fringes like this. This you will get. That is your HRTM image, interference fringes. So basically, the resolution will go as such. Firstly, the lower will be for AFM, then for SCM, and then for TEM. And the second question of yours is, can we get the phase difference data from energy dispersive X-ray spectroscopy method? Phase, uh, EDS basically tells you about the atomic things, that different atoms are present. Phase, for the phase thing, you need to do the imaging like we discussed in this case. Right now, I guess you must have understood that this phase contrast imaging is done to get the information about different phases, this bright field, dark field, and all. I guess your this question is answered from the slides which we are discussing right now. If there is still any doubt, please let me know. Is there any doubt or it is clear? Silva Murugan, are you there? If no, if you have doubt, let me know again. Meanwhile, we'll discuss about the other things. Also, you can have the higher order lower zones. Suppose you are having the diffraction spot. Initially, you will see only the inner region, this region only. This is basically your zero order lower zone, ZOLZ. Okay, I guess your doubt is clear. Fine. Also, you can have higher order lower zones, like the first order lower zone, second order lower zone, and higher order lower zones. So this, the outer diffraction is your first order lower zone. So basically, you remember that the diffraction spot will be uh, shown when it will follow Bragg condition, and Bragg condition will be followed only by those spots which will touch the evolved sphere and all, which we discussed in the previous classes. So the evolved sphere intercepts the point of the higher order lower zones as well. Suppose with this TM, your electron beam has a very high energy, and as a result, your evolved sphere is having a much higher, sorry, your evolved sphere is having a much higher radius, or we can say this your this one having a much higher radius. So if this is your direct spot or incident beam, then you are seeing only these one only, because your evolved sphere is having a much higher radius in the TM mode. And also you can have these first order lower zones, these second order lower zones as well. But in TM, we generally observe this zero order lower zone only. Okay. So when you are tilting the specimen and tilting the beam, these are two different things. So basically, the spots which are touching the evolved sphere only will be diffracted, and for that you need to either tilt the specimen or tilt the beam. So if this is your initial thing, where this is your central beam and your evolved sphere, this one is only touching this 4G diffracted spot, and if you want your other spots to be touched by this evolved sphere, you can either tilt the specimen itself, like you can go from, if this was your initial specimen, you can go from here to here, and you can have this purple one, where now the different spots which were initially like this, those will touch the evolved sphere, and you can have different diffraction pattern. Also, you can have the tilting of the beam. Suppose this is your incident beam, and in this case your incident beam itself is tilted by a certain angle, then also your evolved sphere will change, and as a result your different diffraction pattern will be observed. Also, you have this camera length calibration. This is given by RD is equal to lambda L, where R is basically your difference between the two diffracted spots. Suppose this is your direct spot and this is your one of the diffracted spot, and the difference between the two spots will be given by a value known as R, and your D is basically the D spacing of your specimen, like this one, which you know about the using your XRD and all. And lambda is basically your the wavelength of the electron which you are using. So depending upon the energy of the electron waves you are using, you can have different lambda value. And L is basically your camera length. So camera length is basically the distance of your specimen and the screen. So if you increase the magnification of the lens between the specimen and the viewing screen, we increase the effective distance L between the specimen and the screen. So if you are present in the diffraction mode in your specimen, so if you are in the diffraction, so this is basically a diffraction only, no? So if you are present in the diffraction mode and you are changing your magnification, changing magnification will change the camera length. Okay, so when you are present in the diffraction mode and if you are changing the magnification, that means you are changing the camera length of the diffraction pattern. So this is basically about the CBED only, where you will have the fine probe which will fall on your specimen, and then you will have the diffraction disc rather than the spots. You will have the disc, and that each disc will give information about the specimen. So you can imagine CBED as magnifying the information within the spots in the SAD. So like in the SAD you were getting only these spots, and these are basically the information within the spots itself. So this was basically your one single spot, and now this each spot itself is giving a lot of information. So like SAD, CBED is the most useful technique when you either orient the beam along the zone axis in the crystal to give the symmetrical zone axis pattern, or when you tilt too strong two beam conditions. Unlike SAD, CBD is also even more useful when the probe is deliberately under or over focused. So CBD gives about the information about the specimen's thickness. Lots of crystallographic data such as the unit cell and the associated lattice parameters, the Brevia lattice, the crystal system, the full 3D crystal symmetry, point group and space group, etc. You can get lattice strain measurement using this CBD. Also, you can get the valence electron distribution, the characterization of the defects which are present, the polarity, the enantiomorph. All these informations can be obtained using this CBAD. Now we will discuss in briefly about this STEM mode, then we'll go to the assignment. I'll briefly discuss about this STEM mode. So in this STEM mode, basically I discussed that scanning, transmission and electron microscopy. Don't confuse it with scanning tunneling microscopy. This is transmission, where your specimen is thin and your thin specimen will pass on the electron beams from the specimen, and then you will just, as the SEM where you were having the fine probe, here also you will have the fine probe, and that fine probe will scan on the specimen surface to get the information from the specimen. So the beam must scan parallel to the optic axis. So this is your optic axis. Your beam should not, suppose if this is your beam, it should not tilt like this and this to get the image from your specimen. Rather, the beam must scan parallel to the optic axis at all the time, so that the minimix of the parallel beam in a TM, even though it is scanning. So even though we are doing the scanning in this case, you will not have the beam which is scanning by tilting. So you have this double deflection coils where where you will have this beam only, and it will do scanning, and in this case it will do scanning like this only on all the surface. Okay, so basically in the STEM mode you will have the electron source as similar, and then you will have the condenser lenses, the first condenser lens and the second condenser lens. Then you will have this double deflection coils which will allow your beam to fall on the specimen, and at the other position also it will follow parallel to the optic axis only. It will not tilt. So this is done by the double deflection coils and all. And similar to the TEM, you will have the upper pole piece of objective lens over here after the beam passing from the condenser lenses. Then it will pass through the specimen, and then these convergent beam will pass through the specimen, and then you will have the direct spot in the diffraction pattern, and also you will have the diffracted spot similar to the TM only. Here also you will have the bright field and the dark field images in the TM, where this one is your bright field image and this one is your dark field image. So, and this one is your diffraction pattern. So you can, here you are doing scanning. So in scanning, you can have, sorry, here you are, what's happening? You are doing scanning in this case. So in this scanning, you can have multiple camera at a single, multiple camera for single specimen information. Like this one is your bright field imaging, and then you will have angular dark field, and after that you will have the HADF, which is high angle annular dark field. So you can have different imaging in this STEM mode. So depending upon the angle, so this is your optic axis, and depending upon the angle from which you are getting the information. If you are getting taking these beams, then you will get your bright field imaging. If you are, this will be a donut shape kind of thing. So if you are getting, uh, let me make it clearer. So if you are getting the information from here, this will be bright field. And if you are getting information from here, this will be hollow, and only this will be your detector. So if you're getting information from this will be your annular dark field. And if you further increase the angle and you get the information from this position, this is your high angle annular dark field, HAADF. You can have, depending upon the location from which you are getting the information, you can have different modes. So basically, you can have contrast mechanisms, amplitude contrast, phase contrast, high angular annular dark field, or bright field imaging. All these things can be done in this STEM mode. I guess I am done with the theory part of today. I have in there is one doubt. In STEM, any scattering is happening. What is the difference between elastic and inelastic scattering? STEM, I guess we will discuss much more detail into the next class. I guess today is too late to discuss STEM. Is it fine for you? Because we need to discuss the assignment and only half an hour is left for today's class. Is there any doubt in the theory part which we have discussed today? Can I tell you this in the later class? Because today we don't have enough time. Okay, thank you. Any doubt in today's class? Please let me know. Otherwise, we'll discuss that assignments and quiz. If no, okay. If no, then we'll discuss this practice assignment of week 10. The first question says that the depth of focus in electron microscopy is very high. Is this true or false? This is statement is true. This is completely true. The depth of focus is basically of your imaging part, right? And for your imaging, you have very high region from which you can image your specimen, and the depth of focus is very high in this electron microscopy case. The second question says the condenser lens controls the size and intensity of electron beam in TEM. We have discussed about the role of the condenser lens strength and role of objective lens strength and all. So the condenser lens will control the size and the intensity of the electron beam. Yes, it's completely true. Like we discussed, if the condenser lens strength is increasing, then from parallel beam mode to convergent beam mode, it will go to divergent beam mode, and then after from divergent, it will again go to parallel beam mode. Remember? So this was obtained while increasing the strength of condenser lens strength. So by changing the strength of condenser lenses, the size of probe is changing. Like here it is parallel, here it is point and all. So the statement is true. The third question says to control the beam current and convergence of beam hitting the specimen, dash is used. Can anybody tell the answer of this question? Beam current and convergence is controlled using what? Scanning coil, sample holder, aperture, or detector? Let's discuss this together. Aperture. Yes, you are completely correct. Aperture is the correct answer for this question. The next question says, why TM images have much higher resolution than images from light microscope? So this question you are asking again and again. TM images have much higher resolution. So this higher resolution is due to what? The TM is much greater in size than light microscope? No. The electron traveling as waves have wavelength much shorter than the visible light. This is true. The TM can achieve greater magnification. They are asking why they are achieving. So this is not a correct reason. The fluorescent screen of TM can generate high resolution imaging. So the correct answer is option B. Electrons traveling as waves have higher wavelength. So high wavelength, high lambda means your evolved sphere have a radius 1 by lambda. So higher lambda. Oh, sorry, my bad. Shorter wavelength, small. Small lambda means higher radius, which we discussed just now in the previous slides only. And then you will get a much higher resolution. Your energy is much more, and you can get much finer probe, and as a result you will get finer probe will give you the highest resolution in this case. The last question of this assignment says dash is observed if the sample is bent in a TM bright field image. So if your sample is bent like this, then you will have fringes at grain boundaries? No. You will have Kikuchi pattern? You will always have Kikuchi pattern. You will have bent contours. So there are two type of contours. One is bent and one is thickness. So if your specimen is thick from somewhere and thin from other, then also suppose this is your rod and it is thin from some regions and thick from others, you will get these thickness fringes. And if your sample is bent, then suppose this is your it is bent uniformly, then you will have this bent contours. This bent contours will be clearly visible in your sample image. So option C is the correct answer. Is there any doubt in this assignment? Please let me know. Okay, there is no any doubt, no further doubt. Then we'll start with the quiz of the week 10. The first question says, which of the following statement about TEM is correct? The first statement says, TEM uses electrons to illuminate a sample, producing a three-dimensional image. Three-dimensional image. Please keep this in mind. We discussed in the first slide itself that it gives only a 2D projection, not a three-dimensional image. So this is incorrect. The second statement says TM can achieve a higher resolution than SEM. This statement can be correct. The next question says statement says TM is primarily used for imaging the surface morphology of sample. Is this statement correct? No. It gives only the 2D information, then how it can tell you about the surface morphology of the sample? No, it can't tell. The option D says TM samples are typically thicker than those used in SEM. No, for SEM you can have much thicker sample as compared to TM. But for TM, you need to have your electrons which should be transmitted from your sample. So for the transmission of the electron beams from your sample, you need to have the very thick sample, thin sample. So as a result, if you are having a thick sample, then it will block the electron beams and it will not get transmitted. In SEM, you are basically having scanning from the surface. It will tell you about the topography, about the surface morphology. You can have thick sample over there. But in TM, your electron beam need to pass from your sample and it need to go to your screen and camera to capture. So for that, you need to have a very thin specimen. So here, in this case, I guess option B should be the correct answer. TM should can achieve a higher resolution than SEM. So option B is the correct answer. The next question says, which of the following statements is or are true? Why TM imaging have much higher resolution than imaging from light microscope? They are all talking about the high resolution. And I guess we have discussed a lot about this high resolution and why TM is having this high resolution. So I request all of you to please look at this all four statements and tell me what should be the correct answer for this question. The the statement one says TEM is much greater in size than light microscope. This statement we have discussed in the previous question itself. The next statement says electrons traveling as wave have wavelength much shorter than visible light. Statement 3, TEM can achieve greater magnification. Statement 4, the fluorescent screen of TEM can generate high resolution. Can anybody tell? Rajesh, why you are saying option C? Do you think first statement is correct? TM is much greater in size than light microscope. As a result, it will have a higher resolution. Dep- uh, Depending upon the size, you can't say, na. You need to see how much which technique they are using or which things they are using. We discussed in the previous slide only, previous question itself. Depending upon the instrument size, you can't predict. You can't say that this will be having higher resolution. Is this the reason? No, because eh, yeah, yeah, not don't yeah, yeah. No need to be sorry. We are just discussing the questions over here. We are not having any argument or any. We are just discussing the questions. So you just need to understand why this is correct and why some statement is incorrect. So the electrons which are traveling as a wave have a wavelength which are shorter than the visible light. So according to this, statement 2 is correct. This statement C Statement 3 is also correct. TEM can achieve greater magnification, but this is not the reason. They have asked why TEM imaging have higher resolution. So they have asked about the why, and why reason will not tell you about the magnification. So according to me, option D should be the correct answer. The third question says, which of the following is the correct pathway of electrons in the TEM? You must have known, we discussed when we discussed about the electron source, then how the electron beam is generated from the thermionic field emission, that heat is produced, and then bias voltage is applied, and then uh, it is being converged, and then it is passed through the anodic current to converge the beam. Then it is passed through the cathode, and then it passed through the electromagnetic lens system. Then you all can say it can pass through the sample. Then again, after the sample, also you are having different electromagnetic lenses system. Then it falls on the fluorescent screen. So according to this, option C should be the correct answer. That the beam firstly should pass from your cathode, followed by your electromagnetic lens system, then again sample, then again electromagnetic lens system, then fluorescent screen. Can anybody tell me, electron before the sample also you are having the electromagnetic lenses, and after the sample also you are having the electromagnetic lenses? What are these lenses? You all remember, no? Yes, very correct. Before the sample, you are having the condenser lenses and upper piece of your objective lens, and after the sample, you can have lower piece of your objective lens, and then you can have intermediate lenses, and then in the TN case, you can have intermediate lenses as well as you can have projection lenses and all. So option C should be the correct answer for this case, right? The next question says, which of the following is an advantage of TEM over SEM? This you all can tell. High resolution, faster imaging speed, higher depth of field, or lower resolution. Advantage. I want all of you to respond. This is the third time the same question is coming, and we have discussed all these things in the today's lecture. Yes, the main advantage of TM over STM will be the high resolution. Very good. The next question says, what is the wavelength of electron beam accelerated by a voltage of 100 kilo electron volt without considering relativistic effect? So if you won't consider the relativistic effect, you also then you will have your wavelength given by 1.22 divided by under root of E. Sorry, this is your E. I guess it is visible. So this will be 1.22 divided by under root of 100,000 kilo electron volt, no? So you will convert kilo electron volts to electron volt, and it will give you 100,000 volt. So then you will, can anybody calculate the wavelength and tell me? This wavelength will be in nanometer range. Anyone? Option A, B, C, D? Without, if you are not considering the relativistic effect of your electron beam, then you can directly put this equation where you're not considering the mass of electron and all, then you can directly have your lambda as 1.22 divided by under root of E. Can anybody calculate? Nitin says option C. Yes, you are completely correct. Completely correct. It's 0.0039 nanometer. Okay. If there is no doubt, then I'll move to the next question. Is there any doubt? Or everybody got this answer? Yes, option C is the correct answer. I guess you all got this. This was very easy question. The next question says, before loading the sample, the following software have to be turned on except dash. So if you are loading the sample, your software should be turned on the instrument except which software. So electron gun tilt shift, this should be on. TM imaging and analysis. Analysis will be done later on, no? So I guess this should be the correct option because TM imaging and analysis will be done later on. So there is no need to turn on this software. But you should have digital micrograph, microscope user interface. These two are the basic softwares which should be open on the screen before you put the sample in your TM machine, where the digital micrograph will tell you about the imaging and all, and your microscope user interface will tell you all about all the alignments and all the variables and each and everything which is present in the instrument right now, and how you can change and how you can vary them to make your image much more informative and all. Okay, so in this case, option B will be the correct answer, TM imaging and analysis. Seventh question says, the following statement is true or false. Ultraviolet light is applied to the sample to warm up the sample. This statement is completely incorrect. This statement is answer is option B, false. Because UV light is used for the fluorescent microscopy, not for warming up the sample. UV light is used for the fluorescence microscopy. It is also used for the sterilization and all, uh, for heating the sample, for warming up the sample. Generally, we use directly the in situ heating holders, like we discussed in the slides, or you can have, if you directly need to warm up the sample, then you can use your IR radiations, infrared, infrared radiation to warm up the sample, not UV. The question number 8 says, fill in the blanks. The gun requires the vacuum of the order of what? Millibars or bars. So it requires a generally much higher vacuum pressure. So it's generally in the range of 10 raised to power minus 6 to 10 raised to power minus 7 millibars. So I guess option A will be the correct answer. 10 raised to power minus 6 to 10 raised to power minus 7 millibars. The ninth question says, all of the following are true for both TEM and SEM except dash. The statement one says, the illuminating. This I guess you all will be able to answer, so please listen carefully. The statement one says, the illuminating source is an electron beam. Statement 2. The microscope is focused using electromagnetic lenses and can be used to view specimens smaller than zero point 0.2 micrometer. The statement 3 says the specimen must be sectioned prior to viewing. So, which of these statements is correct for both TEM and SEM? So, and which is and there is one statement which is not correct for both. So you need to identify this and let's try together to solve this question. Are there any comments from your side? Can anybody guess the answer of this question? All of the following are true for both SEM and TM except what? So you need to tell which statement is not correct for both SEM and TM. Statement 1 says illuminating source is an electron beam. This is true for both. Silva Morgan has told his answer as option A, that only statement 3 is incorrect. The specimen must be sectioned prior to viewing. Because in SCM, you can have your specimen without sectioning. But in TM, if your specimen is thick enough, then you need to section your specimen and make it thin enough so that the electron beam can pass through them and then you can have the imaging. The second also says statement says the first statement is correct for both, that electron beam is the source of electron. The second statement says that microscope is focusing using the electromagnetic lenses. Yes, electromagnetic lenses are only used for the electron beams to converge and diverge, and the specimens can be smaller than zero point 0.2 micrometer. Yes, you can see these small samples in your SEM as well as in your TEM. And the third statement is correct only for TM but not for SEM. So, according to me, answer should be A. Only statement 3 is not correct for both SEM and TM. Rest statement 1 and statement 2 are correct for both SEM and TM techniques. The last question of today's class says, which of the following statements is or are true? Dark field image is formed by dash. So your dark field image is formed by what? We have discussed about dark field. I guess you all will be able to answer this question. The first statement says blocking the transmitted beam and allowing the direct beam to pass through. Sorry. Statement 1 says blocking the transmitted beam and allowing the diffracted beam to pass through. For the dark field, if you block the transmitted beam and allow the diffracted beam to pass through, I guess this is what we discussed in the dark field. So this statement is correct. The second statement says blocking the diffracted beam and allowing only the transmitted beam to pass through. This will be your bright field. And right now you are talking about the dark field. So this statement is incorrect. The statement third says tilting the incident beam such that the diffracted beam pass through center and blocking the transmitted beam. So this statement, can anybody tell me which image you will get after this statement 3? Silva Morgan says that option C is the correct answer. Okay. But my question is that if you are using the statement 3 technique, then which image you will obtain? The first one is your dark field. The second one is your bright field where you are blocking the diffracted beam and allowing only the transmitted beam. The third statement says that tilting the incident beam such that the diffracted beam pass through the center and blocking the transmitted beam. Just look at this and then answer this one. The first one is your bright field where you are blocking the transmitted beam and allowing only this direct beam. So this is your bright field. And in second case, this was statement 2. The statement 1 was this one, where you are blocking the transmitted beam and allowing only the diffracted beam. So this is your dark field image. And your third is this one. This was statement 3, where you are tilting the beam. This beam is itself tilted. Now you are getting the beam in this direction, right? Right? So you are tilting the beam such that your diffracted beam is this one and your direct beam is this one. And now you are allowing the diffracted beam and blocking the transmitted beam. Now read again the last statement, which says tilting the incident beam such that the diffracted beam pass through the center and blocking the transmitted beam. So here this one is your centered dark field, right? Am I right? Are you all with me? If you understood that, that means you should be able to answer this question. One has already answered. Any other guesses? Any other comments? This is the last question. We'll dismiss the today's class after this question. So everyone please reply to the answer of this question. Rajesh also says option C, that only statement 1 is correct. Anyone else? Yes, I've got one more answer. Option C. Anyone else? Yes, you all are correct. Only one will be the correct answer for this question according to all of us, because this is the center dark field, this is bright field, and the first one only signifies about the dark field where you are blocking the transmitted beam and allowing only the diffracted beam to pass through. So I guess we are done with today's lecture. If there are any doubts or any comments, please let me know. Yeah. Which one? From assignment or from the quiz? Quiz question number third. This one? This one? Why TM imaging is having higher resolution? This I guess we discussed in 3 or 4 questions in today's class only. You tell. If you were listening, then you can able to tell. According to all of, yeah, the resolution they are talking. Why TM images in having higher resolution? So the size won't matter. The TM is much greater in size than light microscope. This is not the reason for the images to be having higher resolution. The second statement says that electrode traveling as wave have higher wavelength, have shorter wavelength than the visible light. This shorter wavelength will be the reason for having the higher resolution for the TM images. The TM can achieve greater magnification. They are asking why TM imaging. So according to me, I guess statement 3 is a correct statement, but it is not giving the answer of why, which have been asked in the question. This why was asked in the question, no? So this statement 3 is not answering the why. So I guess according to me, statement 2 should be the correct answer. And I guess we all discussed and we came to the conclusion that the answer D should be the correct, that statement 2 should only be the correct answer of this question. Okay.
Okay, okay. Any other doubts? Any other comments? Please let me know. If there are no doubts or comments, then you can leave and I'll end the today's class. Nitin, are you there? Okay, thank you all.